Assalamualaikum everyone, I hope you guys are doing well. So finally I am starting a video series on permutations and combinations of A-level math S1. So what we've done is my team and I, we've gone over all the past paper questions and we have divided permutations and combinations into multiple categories. So what I'll do is first this is going to be an introductory video by the way, but after that I will first cover all of permutations. I've divided permutations into 7 different parts. Okay, you can check out the 7 parts. I'll leave a link in the description where you can download the PDF. You'll find all the past papers with answers, and you'll see permutations and combinations divided into different categories. So we will be solving past paper questions of every single category, and that way we can understand how permutation and combination works and the type of questions that you will be tested on. This video, however, is just going to be an introductory video. So yeah, without wasting any more time, let's start. So permutations and combinations. So if you have done AdMaths in your IGCSE or O levels, you have some idea. But the questions that we have in S1 are actually far more difficult than the ones we have in AdMaths. Okay, so first let's understand the difference between the two. Okay, and then like I said, we're going to study permutation in detail. So let's first talk about the difference between the two. So starting with permutation. Now remember, permutation and combination both have their separate applications, and permutations is basically used when we talk about permutations. So this is basically used when you are selecting and arranging. Okay, so a lot of people say that we use this only when we're arranging. Well, that is true, but before you can arrange something, you have to select what you have to arrange. Okay, so when we're talking about permutations, that is when you have different objects, or even you have multiple objects, and there are some objects that are similar and you want to arrange them. So obviously you're going to first select the ones that you have to arrange, and then you're going to arrange them. Okay, so that is where we use permutations. Now this can be applied to objects. Okay, this can be applied to objects like books, pictures, and what else? Books, pictures. Okay, I can't really think of anything else. But you don't really. There's no restriction as to where we can apply them. This can be applied to objects. It can also be applied to people. Okay, you can use permutations to arrange people in a straight line. It can also be applied to letters. All right, and it can also be applied to numbers. Now, in all these, remember that since we are arranging them, so whenever you're arranging something, the order in which you arrange matters a lot. Okay, so here, remember that the order is important. All right, now, to give you an idea of how permutations basically work and what exactly do I mean by order, now let's say there are 3 people who have participated in a contest, and there are 2 judges. Okay, so let's say there is judge 1, and judge 2. Okay, now there are the 3 people who have participated, or the 3 people who have been shortlisted for the podium, or that, which basically means first, second, third, are A, B, and C. So judge 1 says that as per my judgment, I think A should get the first place, C should get the second place, and B should get the third place. Okay, so this is the ranking order as per the first judge. Now judge 2 on the other hand says that nope, I think B should get the first place, A should get the second place, and C should get the third place. Now because we have rankings attached to these people, so which means the order is important. So can we say, well, they're both the same? I mean, both the judges have shortlisted the same 3 people, so it doesn't really matter who gets first, second, and third. Can we say that? Of course we can't. Why? Because here the order is important. Why? Because we're arranging them. We're arranging first, second, and third place, so that is why the order is important. So another example would be, let's say that you have a 4-digit password to your iPhone. Okay, and let's say the password is 2357. So if somebody just tells you the numbers to the password, like the numbers are 5327, is that enough? Can you then, well, technically after multiple tries you can figure out what the correct password is, but the thing is, you can't just enter the correct digits in whatever order and expect to unlock the phone. You have to get the order right as well. So here, technically, the concept that we're using is permutations. Why? Because changing the order leads to a different password. All right, so remember, long story short, in permutations, AB, that is arranging 2 objects, A and B, as AB is not the same as BA. Okay, But when we are talking about combinations on the other hand, so in combinations, what we're doing is we're just selecting only. We're not arranging them, we're only concerned with selecting. And this is usually done when you are making a team. Okay, why? Because if you're making a team, then in that case, the order in which you make the team is not important. The order is not important. All right, and in the case of combinations, AB, that is two people who are A and B respectively, is the same as BA. Why? Because these are the same people. So let's say somebody says that, you know what, I want 2 players for the upcoming table tennis tournament, and the players that I choose are AB. And then somebody else comes and says that, you know what, I don't like the people that you've chosen, I want BA. Well, does that really make sense? No, it doesn't. So should there be a debate over this? No, because it's a team. It ultimately doesn't matter. However, if you're making a team, but within the team, there is a certain merit, like, for example, who's going to be captain, who's going to be vice captain. So let's say if here they're not just making a team, but they're also deciding who's going to be captain and who's going to be vice captain, then A being captain and B being the vice captain is not the same as B being captain and A being the vice captain. Okay, so whenever you have some sort of merit, some sort of ranking that's involved, and you're making a team, then in that case, we use permutation. Okay, but if there is no merit, no ranking, so that is when we use combination. So coming back, since these are the same people, coming back to the point, since these are the same people, therefore it's considered the same team. Okay, now what we're going to do is we're going to put permutation and combination, we're mainly combination on the back burner for now, and we're going to focus on a prerequisite of permutation, which is basically called factorial notation. And that is this factorial key that you will have on your calculator. So if you press shift and if you press the button that's right next to sign, you will see an exclamation mark. Now that's not exactly an exclamation mark, it's called factorial, and we'll understand how it works. So let's say, here's a question which we can solve through factorial notation, and not just through factorial notation, we can also solve it through permutation. Okay, so we're going to understand how they're both kind of the same and used interchangeably. So it says, how many ways can 3 people be arranged in a straight line? Now notice that the keyword here is arrange. So what we have to do is we have to arrange them. And whenever we are arranging people, the order in which we arrange them is important. Okay, so a good way to start would be, now, if you know the concept already, you probably have figured out the answer immediately, but let's manually find out the number of ways that actually we can arrange them. So I'm going to call one person A, the other B, and the third person C. Okay, so let's make 3 blanks and let's write down one by one all the possible ways in which we can arrange them. So one obvious way is obviously A, B, C, but is this the only way that I can arrange these 3 people? Of course not. Another would be, let's say A, C, B. So I've kept A in the same place, but I've shuffled B and C. Another would be, let's say we keep B in the first place, and then A in the first, and C in the second, and C in the third. Now let's see if there is another possibility. Of course there is. It could be B, C, A. Now what if C wants to be in the first place? So in that case, we would have C, A, B, and notice that we can shuffle A and B. So that would make it C, B, A. Okay, now let's count 1, 2, 3, 4, 5, 6. Now I encourage you to think of any other possibility, and with a bit of thought, you'll realize that there isn't. So altogether, you can see that we have how many ways? That we have 6 different ways in which 3 people can be arranged in a straight line. So does that mean that every time we have a question like this, we have to do it like this? Of course not. There is an easier way. So the easier way is, the shortcut is that you make 3 blanks, since we have to arrange 3 people. 1, 2, 3. Now, for the first place, we have 3 options because nobody has been arranged yet. All 3 people are available to be arranged. That means in the first place, we have 3 options. Now, in the second place, since one person, whoever it may be, A, B, C, has been arranged or has taken a seat, now we have to look for the second place, for which we have 2 options. And then lastly, for the last place, we have 1 option. So that means altogether, all I have to do is simply multiply them. So that would be 3 times 2 times 1, which is equal to 6. Okay, so now this is also called the basic counting principle. That is, if you can do task A m number of ways and task 2 n number of ways, then together these 2 tasks can be performed m into n number of ways. Okay, just like if you remember going back in O levels, if let's say you roll 2 dice, and you want to find out the total number of outcomes. So since there are 6 outcomes, 6 different outcomes in die 1 and 6 different outcomes in die 2, together you have 6 times 6, which is 36 outcomes. Similarly, if let's say you toss a coin and you roll a die, a fair 6-sided die, then altogether you would have 12 different outcomes. Why? Because 2 in the coin and 6 in the die, so 2 into 6 is equal to 12. So this is kind of like basic counting principle also, but the reason why we have termed this as factorial notation is because 3 into 2 into 1 is basically the same as 3 factorial, which is 3 into 2 into 1, and that's equal to what? That's equal to 6 ways, okay? Now, or you may be thinking that where does permutation fit into this? So this can be done using permutation as well. So for permutation, the key that we use is P, which you will find on your calculator if you press shift and then if you press the multiplication key. So I don't think if this is in focus, but you basically see a P on your calculator. Now, how do we use this, or how can we use permutation over here? Very simple. How many people do we have available that are to be arranged? That's 3. And how many people do we have to arrange of the 3? We have to arrange all 3 of them. So that would be 3p3, which is the same as 3 factorial, or 3 into 2 into 1. And that's equal to what? That is also equal to 6. Okay? So this is what factorial notation is. We'll write down formally what it is, as in what the definition is. But first, let's understand its application further, and let's do some more examples. So here's a question which says, how many ways can 5 people be arranged in a straight line? So here we're talking about 5 people. So with 5, we can't do it manually the way we did it with 3. So instead, we are going to use a shortcut. So 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. Yeah. So for the first place, we have 5 options. For the second, 4. For the third, 3. For the fourth, 2. And for the fifth and final place, we have 1 option. So that means altogether, that's either equal to 5 factorial, which is 5 into 4 into 1, or 5p5, which is equal to, well, you can work this out. You'll notice that it's 120. And you can see why we didn't do it manually, because had we done it manually, I would have only been able to solve this question in this video. Okay, now part B. Part B says, how many ways can 3 of 5 people be arranged in a straight line? Okay, so now we have somewhat of a restriction. Okay, the restriction is that I don't have to arrange all 5 of them. I only have to arrange 3 of the 5 people. So that means in the first place, I have 5 options. In the second place, I have 4 options. In the third place, I have 3 options. So altogether, can I say 5 factorial? Nope, obviously not. It's 5 into 4 into 3, 5 into 4 into 3, or we had 5 people available to be arranged, and of these 5 people, we only had to arrange 3. So that means we can do 5p3. Let's see what the answer to that is. So 5p3 is equals to 60. So that means if you want to arrange 3 people out of 5, you can do that through 60 different ways. Okay, now, what is it? What is factorial by definition? Here, as you can see. So I'll write down over here that this is the definition. Okay, product of all positive integers less than or equal to n, where n is a positive integer. So that means if you have n factorial, you would do n into n minus 1 into n minus 2, and you'd keep on doing this, till you get 3 into 2 into 1. Okay, so we start from n and we keep on going till the very last positive integer, which is 1. That is if it's n factorial. And what does it represent? It represents the number of ways n different objects can be arranged. Okay, now let's do some examples. And we saw that how permutation was applied to arranging people. Now let's see how it can be applied to arranging letters. Okay, now I want you to observe something that's very important over here. So it says, how many ways can the 3 letters of the following words be arranged? Now in the first part, it's Ali. How many letters do we have in the word Ali? 3 letters. So that means you can list down all 3 different ways, or you can just do 3 factorial. Why? Because for the first place, you have 3 options. For the second place, you have 2. And for the third, you have 1. So 3 into 2 into 1, which is equal to what? Which is equal to 6 ways. Okay, now, next we have the word Bob. Now notice that there's something interesting with the word Bob, and that is you have 2 letters of the same kind. Okay, so how does that work? What do we do when we have 2 letters of the same kind? Well, let's start by making 3 boxes. And what if I do 3 into 2 into 1 using the same principle as we did with Ali, and say that we have 6 different ways in which the word Bob can be arranged. Now let's see if we can list those 6 ways, okay? So I want you to pay close attention. So I'm going to make 6 blanks. 1, 2, 3. Oh, sorry, not 6 blanks. I'm going to make 3 blanks 6 times. 1, 2, 3, 1, 2, 3, 1, 2, 3. So that's 5, 1, 2, 3. Okay, now let's start with the one arrangement that we can see already. That's BOB. Now, what if I swap the B's? Okay, I move this B here and this B here and say, you know what, here's another arrangement, and that is Bob. Now, what would you say? You would say that, wait a minute, this is not exactly the same arrangement, it's the same. Okay, so we will count this as 1. So even though we've swapped the B's, but it's Bob was still Bob and it's still Bob. And let's write down another arrangement, which is BBO. Since it's different from Bob, that means this will be counted. But what if, once again, I swap the 2 B's and I say that, you know what, here's another arrangement, BBO. So once again, these two are one and the same. So that means this is these two basically are together is another unique way of arranging these 3 letters. Now, what if I say that we can do OBB? And then once again, I swap the B's, so you'd barely notice the difference. So that means these two are the same. And altogether, there are how many ways? There are 3 ways in which the word Bob, in which the letters of the word Bob can be arranged. Now, the question is, how do we do this without actually listing it down? Well, very simple. All you do is, in the numerator, 3 factorial. Okay, but in the denominator, what you do is, since there are B's that are being repeated, so you divide it by 2 factorial. Why are we dividing it by 2 factorial? Because 2 factorial represents the factorial of the number of same objects. It represents the factorial of the number of same objects. Okay, so this brings me to a very important note also. Now let's make some room here. Oops. Yeah, so here's the note. I want you to pay close attention. The note is that when letters slash objects are repeated, when letters or objects are repeated, we divide by the factorial, of the number of times they are repeated. Okay, now I'd like to show you the general way of doing this. Okay, so let's generalize this, and for that we can write down the official definition. Here it is. So it says the number of distinct arrangements of n objects in a line of which p are identical to each other, q are identical to each other, or of a third type are identical to each other is n factorial divided by p factorial divided by into q factorial into r factorial. Okay, now let's apply the same concept to the letter to the letter in the word trigonometry. Okay, so how many letters do we have altogether? We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So that would be 12 factorial. But what if I leave it there? Obviously, that'll be wrong because there are so many letters that are being repeated. So we can see that the word T occurs twice. Okay, so what just happened? I have no idea. Anyway, so we can see that the letter T occurs twice, so that means we have to divide by 2 factorial. So this 2 factorial is representing the number of times the letter T has been repeated. Now R is also occurring twice, so that means we have to divide by 2 factorial. So this 2 factorial is basically for the 2 R's, and O also is another letter that is being repeated, so that means we have to divide by 2 factorial as well. And then if you work this out, you will get a huge answer, and normally you do get some really huge and crazy values in permutations and combinations, so that's perfectly all right, don't freak out. It's 59,875,200. Okay, so this was just a concept where you have objects that are being repeated. Now, what we're going to do next is we're going to do some questions where we will come across some restrictions. Okay, so here's the first question. Let's see what it says. So it says, find the number of ways in which all 5 letters in the word great can be arranged. So notice that in the first part, there is no restriction. So that means, and there is no letter that's being repeated. So that means the answer to the first part will simply be 5 factorial, which is equal to 120. Now, in the second part, let's see what it says. How many of these arrangements are the letters? How many of these arrangements are the letters A and E next to each other? Okay, so what we're going to do is we're going to put A and E together. We have to make sure that they're next to each other. Now, whether they are in the first and the second place, or the second and the third place, or the third and the fourth place, or the fourth and the fifth place, that does not matter as long as they are together. Okay, so how do we do questions like these? Now, there is a standard way of putting objects together, which is, by the way, one type of question which we're going to do in detail. We're going to do multiple possible questions of, but for now, for starters, here's what you guys need to understand. So make 5 blanks, since there are 5 letters in the word great. Put the 2 letters that are supposed to be together, which are A and E, in a box. Okay, when I say in a box, that means you basically, since these are 2 letters, you're going to obviously have 1 letter per blank, but we're going to make a small box around it so that we make sure that they can stay together. Okay, now if you think about it, A and E can shuffle amongst themselves. I mean, there's nothing in the question which says that A has to come first and then E. So that means I can shuffle A and E, and since these are 2 different letters, I can shuffle them 2 factorial number of ways. Okay, so this is what's happening inside the box. But like I said, since A and E have to be together, and there's nothing in the question which says where they should be together, so that means we can have AE anywhere. Okay, so how do we take that into account? So now what we're going to do is we're going to treat AE as 1 unit. Okay, so if I treat AE as 1 unit, how many units or how many different objects or we're not going to call them letters, okay, but how many different objects or units do I have to arrange? So here's 1 unit, which although is made up of 2 units, but we don't have to worry about that. Here's the second, here's the third, here's the fourth. So that means we have 4 different units which we have to arrange. And how do you arrange 4 objects or 4 people or 4 letters or 4 units in a straight line? You do that by simply doing 4 factorial. So that means you have 2 factorial multiplied by 4 factorial. Okay, so this 2 factorial, I repeat, is representing what's going on inside. That is basically considering AE or EA. And this 4 factorial is representing what's going on outside. Okay, and outside, if you look at it, you have 4 different objects which you have to arrange, and you can do that 4 factorial number of ways. Okay, now let's see what the answer to that is. The answer to that is, well, let's work it out. 4 factorial times 2, which is equal to 48. So that means you can arrange, of these 120, 48 arrangements are such where A and E are next to each other. Okay, so there you go. Now, before I move on to the next part, there's one thing that I would like you to understand. That is, I'd like you to understand what is the logic behind this 2 factorial into 4 factorial. So basically, here's what we're doing. Let's duplicate this. Let's bring it here. Okay. Now, if you think about it, let's not use the 4 factorial approach. Instead, there's another approach which I would like you to understand, and then that will help you understand this 2 factorial into 4 factorial approach. So as far as AE is concerned, we can shuffle them 2 factorial number of ways. Okay. Now, for a minute, if I only focus on these letters, okay, so here we can see that we have 3 different letters here, okay, and we can arrange them how many ways? We can arrange them 3 factorial number of ways. But like I said, there's nothing in the question which says that A and E have to be in the first place, okay? They can be in the second, third, fourth, wherever, basically. So that means it's possible another arrangement while satisfying the restriction would be, and do keep in mind, by the way, I should have mentioned this in the beginning, that whenever you have a certain restriction, make sure that you always fulfill that restriction first. Okay, so whenever there's a certain restriction, make sure that you fulfill that restriction first. Okay. So another possibility would be that I first have any other letter other than A and E, and then I have AE. Okay, so that means now we can see 2 different ways in which AE can be together. Another possibility would be, let's duplicate this, that we have 2 blanks, okay, where we can have 2 letters other than A and E, and then AE, and then the final letter. Another possibility would be, if I duplicate this, that first we have 3 different letters, okay, and then we have AE. Now, if you think about it, how many different ways do we have AE together? We have 4 different ways. So that means if we're using this approach of 2 factorial into 3 factorial, we have to multiply this by 4 because there are 4 different ways or 4 different places where A and E can be while still being together. So if you think about it, what's 3 factorial into 4? That's basically 3 into 2 into 1 into 4, which is as good as 4 into 3 into 2 into 1. So that is why we do 2 factorial into 4 factorial. That's why we did 2 factorial into 4 factorial earlier. Notice that it leads to the same answer, that is 48 ways. But I obviously don't recommend this approach, okay? Not because it's wrong, because it's lengthy. This is the approach that I recommend, and this is the approach that you will find in most of the books, okay? So I hope that's clear. Now let's do another example, and here it is. So let's see what it says. It says, how many arrangements of the word achieve are there if there are no restrictions? Okay, so the first part usually, not all the time, but usually has no restrictions, okay? So the only thing that we have to worry about is if there is a letter that's being repeated. So altogether there are 7 letters, and we can see that the letter E is perhaps the only letter that's being repeated. So we divide by 2 factorial. If you do this right, you get 2,520 as your final answer. Okay, now let's talk about part 2. In part 2, notice that the question says that the first letter is in A. So what the question here has done is it has fixed the position of one letter. So we make 7 blanks, 1, 2, 3, 4, 5, 6, 7. Yeah, that's it, 1, 2, 3, 4, 5, 6, 7, okay? Now an important note, which I should have written earlier, and that is note. Okay, that we shouldn't have 2 colons. So the note is that whenever there is a restriction, make sure to first settle that, okay, or settle/satisfy that. So whenever you have a particular requirement, make sure that you first fulfill that before you do anything else, okay? So like here, for example, the first letter is an A. So I got to make sure that the first letter is an A. Now, as far as the remaining 6 are concerned, notice that we have 6 remaining letters, okay? But do keep in mind that of the 6, we still have the 2 E's somewhere in these 6 letters, so we have to divide by 2 factorial. Now here, since we just have A fixed, we don't really have a lot of options other than just 1. So you can do 1 into 6 factorial divided by 2 factorial, okay? Or you might as well completely ignore this 1, and you would get basically 360 different ways. And that's the answer to the second part. Now let's see what the third part says. The third part says that the letters A and I are to be together. Okay, so how can we do that? How can we keep A and I to be together? So very similar to the question that we just solved. 1, 2, 3, 4, 5, 6, 7. So let's place A here, let's place I here. Now these 2 are to be together, which means that they can shuffle amongst themselves. There's nothing in the question which says that A and I are to be together in that order. There's nothing of that sort, although in some questions there will be, so watch out for that. So that means we have 2 factorial, which is considering the number of ways these letters can shuffle amongst themselves. Now, what are the total number of units that we have to arrange now? That's 1, 2, 3, 4, 5, 6. So that means 2 factorial multiplied by 6 factorial, which is equal to what? Well, wait a minute, not just 2 factorial into 6 factorial. Don't forget that amongst the remaining 6 letters, there are 2 E's that we are repeating. So in order to make sure that we don't end up counting them as multiple arrangements like we did with the example Bob, we had divide by 2 factorial. So what do we get? We get 720 ways. Okay, now let's do part 4. Part 4 says the letters C and H are to be apart. Okay, now notice there are 2 objects, 2 letters that we have to make sure are not together. Okay, now what we're doing right now is something that applies to 2 objects. That is, the number of ways that they are apart is equal to the total minus the number of ways that they are together. Okay, so as far as 2 objects are concerned, they're either going to be together or they're not together. Okay, there's nothing in between. So, and since in the previous part where we figured the letters A and I are to be together, and in this part, we're figuring out the letters C and H are to be apart. So that means if I want to find out the number of ways that C and H are to be apart, I need to first find out the number of ways that they are together. Now, if you think about it, let's do the working for that. Let's find out the number of ways that they are together. If you've already thought of what I am going to say, then that's great. 1, 2, 3, 4, 5, 6, 7. Okay. Now, the working for keeping C and H together, like I said, if you think about it, is not going to be any different from the working for A and I to be together. Why? Because 2 letters, although different, but the number of letters are the same. So you do 2 factorial for C and H, and for the remaining you do 6 factorial divided by 2 factorial, since we have to divide by the number of letters that are repeating, and we would get the exact 720. Okay, now 720 is the number of ways that they are going to be together. And what's the total? The question has already made us work out the total, which is 2520. So 2520, the number of ways that they are, that they can be arranged, minus the number of ways that they are together, and that gives us 1800 ways. So that means there are altogether 1800 ways in which C and H are to be apart. So what I was going to say was that you don't really have to do this working, because we've already done it for 2 other letters and it's going to be the same. So all you got to do is together a total minus the number of ways that they are together, which is equal to the number of ways that they are going to be apart, which is 1800. Okay, now let's do the last example. This example says 3 girls and 2 boys are to be seated in a row. Find the number of different ways that this can be done if the girls and boys sit alternately. Okay, so 3 girls and 2 boys. So that means we have altogether 5 people. So let's make 5 blanks. 1, 2, 3, 4, 5. Okay, now what should I start with? What if I start with a boy and then girls, considering that they have to sit alternately, and then a boy and then a girl and then a boy? Is this possible? Let's see. Well, this means that we have to have 3 boys and 2 girls. Well, as far as 2 girls are concerned, we can do that since we have 3 girls, but where will I get the 3rd boy from? So that means this is not possible. So how do we make it possible? Well, we start with a girl. So 1, 2, 3, 4, 5. So if I have a girl in the first place, then I got to have a boy in the second, and a girl in the third, and then a boy in the fourth, and then a girl in the fifth. Okay, so if you think about it, for the first place, we have 3 options as far as girl is concerned, and for the next girl, we have 2 options, since we have 3 girls altogether, and then for the final girl, we have 1 option. And then as far as the boys are concerned, we have 2 options for the first one, 2 options for the first one, and 1 for the last one, the second one. So altogether, if you think about it, it's basically 3 factorial for the girls multiplied by 2 factorial. You don't necessarily have to write factorial. You can do 3 into 2 into 2 into 1 into 1, the way that you see it. And either way, the answer is going to be 12 different ways. Okay, so here also you can see that this is a certain type of question where position of one or even multiple objects is fixed. Okay, so that's the answer to part A. Part B says a girl sits at each end of the row. So once again, you can see the condition is that position of 2 people are already fixed by the question. So you got to have a girl in the, actually let's write it down. You got to have a girl in the first place and a girl in the last place. So how many options do you have, since we have to settle the restriction first? So for the first place, we have 3 options, since there are 3 girls to choose from. And in the last place, we have 2 options. Why? Because we have 2 girls to choose from. Now, what about in between? In between, anything can happen, and we don't really care because we have met the restriction, or we have satisfied the condition that was placed in the question. So we are now left with how many people? Let's see. So we had 3 boys and 2 girls to start with, so that was 5. Now from 5, 2 girls have already been arranged. That means now we're down to 3. So we have to arrange 3 people from 3 people. Okay, so we have 3 people to arrange, and we have to arrange all 3 of them. So that can be done 3 factorial or 3p3 number of ways. So that means 3 into 3 factorial into 2, which is equal to 36 ways. No, yeah, 36 ways. 36 ways. All right, now part C. Part C says the girls sit together and the boys sit together. All right. So once again, let's make 5 blanks. 1, 2, 3, 4, 5. So the girls have to sit together. So that means here we have the girls sitting together. Girl, girl, girl. Okay, now you might think that these are 3 girls, and so why aren't we dividing by 3 factorial? Well, since they're 3 different people, we're not going to consider them as repeated objects. Okay, so that is something that's done when we're using numbers, since if let's say you have 2 2s, so 1 2 is the same as the other 2, or if let's say you have 2 p's, 1 p is the same as the other p. But when you have people, even if let's say you have 3 girls or 4 girls or 5 boys, we're not going to say that, oh, because the boys are being repeated, let's divide it by the number of times they're repeating and the factorial of the number of times that they're repeating. Okay, so every person is different from another, basically. That's the reason why. So in this box, we can have 3 girls, okay? And remember that they can shuffle amongst themselves. So how can they shuffle amongst themselves? 3 factorial, okay? Or if you want to see the working behind it, so here we have girl 1, girl 2, girl 3, and since they can shuffle amongst themselves, so that would be 3 factorial. Here we will place the boys, since the question says that the girls and boys are to be together, so boy 1 and boy 2, and these boys, obviously there's no restriction as to why they can't shuffle amongst themselves. As long as they're together, that's all that matters. Also, another thing that we have to consider is that the question doesn't say that the girls sit together and the boys sit together in that order. That means you can have all the boys sitting together first and then all the girls. So that means we now have to consider them as 2 different units and find out how many ways these 2 units can be arranged, which will basically be 2 factorial, okay? So 3 factorial times 2 factorial times 2 factorial is equal to what? So that's 4. I don't encourage that you work this out mentally. It's best that you use your calculator. 3 factorial times 2 times 2. So that's equal to 24 different ways. All right. So yeah, that's it. That's it for this video. I hope you guys have understood, and I hope you guys have understood the basic idea behind permutations and combinations. In the next video, what we're going to do is we're going to pick a specific type, which is type 1, where the position of one or more object is fixed, and we're going to focus solely on those type of questions, and we're going to be doing questions from past papers. The questions that I solved in this video were not from past papers, they were from different books, just so that you can sort of get yourself introduced to the idea, and I hope it's clear now. So that's it for this video. I'll see you guys in the next one. Until then, take care. Bye-bye.